Hi, welcome to the lecture 50 in the course Classical Mechanics 1. In last few classes, we discussed canonical transformation, and then last lecture we have started two-body central force problem. So, let me recap some points of two-body central force problem. Then we will start today's lecture. Okay. So, central force means that potential from which the force is obtained depends only on the magnitude of the position vector. It does not depend on the direction. So, this is the central force, and in last lecture we considered the two-body central force problem. So, let me recap little bit. So, we considered two-body central force problem. So, say this is my particle 1 at position vector 1, and then this is my particle 2 at position vector r2. And then we last lecture we have shown that this system can be reduced to effective one body problem by considering the center of mass and the relative coordinate. So, center of mass coordinate and relative coordinate. Okay. So, in relative coordinate, center of mass we have seen. So, let me write the Lagrangian. So, Lagrangian with respect to two body was half m1 r1 dot square plus half m2 r2 dot square, and since the force is central force, so it depends on the magnitude between r1 and r2. So, this was the Lagrangian for two body system. We reduce this to center of mass and relative coordinates, and reduced Lagrangian was half m r dot square plus half mu r dot square r vector dot square, and then you have the u r, where r was your this coordinate, relative coordinate, and capital R is the position vector of center of mass. But now you can look at this Lagrangian. Center of mass is free to move because it is not appearing in the potential energy. So, the motion of the center of mass is just a free motion. So, free motion for center of mass so that is not interesting. So, we will only focus on the relative coordinate, and forgot to mention mu is the reduced mass of the system. Mu 1 over mu is 1 over m1 plus 1 over m2, which is the reduced mass. So, effectively what we gain, that two body problem has 6 degrees of freedom, we reduce it to a 3 degrees of freedom. In that, a particle having reduced mass of the system moving with the potential which depends only on the relative position. Okay. So, the whole two body problem now boils down to effective one body problem. This we have learned in last class. Also, we have seen that the center of force problem, the motion takes place in on a plane. So, motion in center force problem, motion is always on a plane. Okay. And then we characterize a plane with the x and y coordinate, and effectively we found that the one body effective Lagrangian is written as half mu r dot square plus r square theta dot square u r. R theta characterize the plane. R is the going to 0 to infinity and theta 0 to pi. So, it characterized in the polar coordinate, it characterized the plane. Okay. So, this was the our Lagrangian, and immediately we observe few important consequence. First of all, that we observe theta is cyclic. Theta is cyclic implies p theta, the momentum conjugate to theta, is conserved, and which we calculate del L del theta dot is mu r square theta dot, which is nothing but angular momentum, which we denoted in last lecture by m. Okay. So, we obtain that even it is a two coordinates appearing in this Lagrangian, we found that one of the coordinate is cyclic and you have the angular momentum is conserved. So, for any central force problem, angular momentum is conserved. Okay. Okay. So, this was our observation. Up to this we discussed in last lecture. Now, today we will see that even for any central force problem, that aerial velocity also will be a conserved quantity, that we will see. So, let us consider that suppose this is the trajectory of a particle in the center force motion, and so so this is your position vector r, and this is r plus dr after some time, and this angle is theta, this angle is theta plus d theta. Okay. And particle moving along this trajectory, this trajectory. So, now if you look at that quantity, that area covered in some infinitesimal time dt, this is the area covered by the particle. Okay. And this area, if we calculate, suppose this quantity will be your r d theta. So, the area, if we consider a triangle of this, let me use a different ink, this and this triangle. So, that will be the area covered in the infinitesimal time dt. So, dA will be the area covered in time dt will be the area of this quantity, which is half r times r d theta. This is the r and this is r d theta. So, dA dt, the rate of change of area will be half r square d theta dt. Okay. So, half r square d theta dot. But we already have seen that angular momentum is conserved. What is angular momentum? Angular momentum was m mu r square theta dot. So, if we substitute theta dot, so theta dot will be m by mu r square. So, this will be half r square m mu r square. Okay. So, the aerial velocity of the particle under central force problem will be half the angular momentum by the reduced mass, and this is a constant. Okay. So, we observe that in case of central force problem, our angular momentum is conserved and also the particle swept out equal area in equal time. Okay. So, this is the two important feature of the central force problem. Okay. So, now let us see, is there any other constant of motion in the system, and for that let us calculate the equation of motion. So, let me repeat, the Lagrangian was half mu r dot square plus r square theta dot square to u r. So, equation motion for the radial coordinate r, we can write d dt of del L del r dot minus del L del r equal to 0, the Euler-Lagrangian equation. Okay. Now, for this Lagrangian, if you calculate Euler-Lagrangian equation, you will get mu r double dot, because del L del r dot is mu r dot, minus mu r theta dot, this is coming from del L del r plus del u del r equal to 0. Now, if you substitute theta dot in this equation, then you will get the equation motion for the particle, because we already have seen that mu r square theta dot is your angular momentum. So, theta dot we substitute as m by mu r square. So, we get equation of motion by substituting this mu r m mu, yeah, this is theta dot square. So, m mu r square whole square plus, okay. So, mu r double dot minus m square mu r cube plus del u del r equal to 0 is the equation motion for the particle, the particle having the reduced mass. So, two body central force problem was reduced to one body problem with the effective mass, and that imaginary particle will have this equation of motion. Okay. Okay. So, now if we consider this, rewrite this equation little bit in this form, then we can find that the total energy of the system is also conserved. So, that let me write this equation in this form. So, if I take mu r double dot equal to, I can write, taking right side, del del r of u, so minus minus del del r u plus m square to mu r square. Okay. Because if we differentiate this term, it will be minus 2 by r cube. So, that will give you the m square, and 2 and 2 get cancelled, minus signs, this will be minus minus plus sign. So, this. Okay. And the right hand side, left hand side rather, left hand side I can write ddt of mu r dot, and if we substitute del del, okay, before that, okay, before writing that, let me multiply both side by r dot. Okay. So, right hand side, left hand side I can write half mu r dot square ddt, that will give you the mu r dot double dot r dot. Okay. And the right hand side, see, I can write del del t is del r del t times del del r. Okay. So, ddt can be written r dot del del r. Okay. So, this I can write ddt of u plus m square 2 mu r square. Okay, it's clear. So what we did, this is the equation of motion, and the equation of motion I multiplied both side by r dot. So from here to here, multiplying both side by r dot. Okay. So this, now I can combine this together, bringing all terms to the left side, ddt of half mu r dot square plus m square to mu r square plus u equal to 0. That means this quantity implies this quantity half mu r dot square plus m square to mu r square plus u r is constant. So, and this is the nothing but the total energy of the system. Because this is the kinetic energy, this is appearing due to the conservation of angular momentum, and this u is the potential energy. Okay. So this is the total energy. So we obtain, so far we obtain angular momentum is conserved, m equal to mu r square theta dot, and E equal to half mu r dot square plus m square 2 mu r square plus u r. Okay. So two equation of motion. Okay. So let me repeat. So far we have seen that two characteristic of central force problem. One is that any central force problem, angular momentum is conserved, and also the aerial velocity is a constant, independent of the structure of the potential, whether particle moves in a closed orbit or in a kind of thing, or independent of the potential u r, you find, we prove that aerial velocity is conserved. Now here we find that total energy, expression for the total energy, which is also conserved for this system. Okay. Now when we find a solution of a central force problem, we need to integrate these two equation to find the integral solution. Okay. So to obtain that, let me write these two equations. So let me have a number. So this equation number 1. So from theta dot, we can write theta dot is, we can write angular momentum by mu r square. So if we integrate theta, so d theta will be m mu r square dt, and if you integrate, you will get theta equal to theta dot plus integration m mu r square dt. Okay. So this is equation. We will simplify this equation further. Okay, and 0 to say some time t. Similarly, we can write also the r dot will be, so E minus m square 2 mu r square minus u r, and then this will be multiplied by 2 by mu and then square root. Okay. So this will be the r dot expression for r dot. Okay. So we will be using these two in writing the integral of motion. Okay. So dt integration we already have. So dt we can from here also we can find. So d r dot is dr dt. So we can have that r dot equal to this. So dr dt, dt equal to, so dt equal to dr by root over 2 by mu e minus m square to mu r square u r square root. Okay. So this dt we can use in the d theta expression, and theta we can find. So if we substitute this in this equation, we will obtain d theta will be m by mu square, m by mu r square, then dr by root over 2 mu e minus m square to mu r square u r square root. Okay. This is your d theta equal to m mu r square dr to mu. Okay. And you can simplify little bit. So theta equal to theta naught plus integration, let me write dr by r square, and then this if you take inside, then mu will be inside. So 2 mu square, mu will be inside, so 2 mu square, and by m square mu times e minus m square 2 mu r square minus u r. So let me have a well known form of this integration of motion. So if we write this, I hope I have writing everything clearly. Okay. So this will be theta 0 plus r2 r0 to r dr by r square, and then this square root, if I take inside 2 mu e, because this will get cancel, and 2 mu e by m square, or m square, okay, by m square minus 1 over r square minus 2 mu m square u r, or if you want you can take the m square outside. So both form is well accepted, so no problem. So this is the form of the integration which we need to integrate when we will solve this problem. Okay. So now we want to focus, we will come back to this equation later when we will discuss Kepler's problem, and solution of this integration will give you the solution to the central force problem, but without solving this integration, we can qualitatively predict the trajectory of the particle or motion of the particle. Okay. So for that reason, we will need to consider the one particle motion, and I will now discuss how one can predict, just looking at the potential, the trajectory of the particle. So let us consider the particle. Now it is Lagrangian. Let me start with Lagrangian. So again with the different ink. So So Lagrangian half mu r dot square plus r square theta dot square minus u r. So let me write this by substituting theta dot r dot square. Theta dot, remember, is m by mu r square. Okay. So you will have plus r square m square by mu square r to the power 4, okay, and then u r. So this half mu r dot square plus m square 2 mu, because 1 mu will get cancelled with mu square. So 2 mu r square minus u r. Think of this as a single particle. This can be thought as a single particle in one dimension, is moving under a effective potential let us denote with U effective equal to U r minus m square just a moment, there is a sign problem. Okay, from this point of view, it is what I wanted to say is not clear. Okay, so the total energy. So okay, so let me not put this argument. Total energy was half mu r dot square plus m square to mu r square plus u r. So this is the effective U effective, so effective potential energy. So this problem we can think about that a particle in one dimension moving with effective potential, the effective potential U effective equal to m square to mu r square plus u r. Okay. So now looking at this effective potential, we can predict the trajectory, possible trajectory of the particle. So that we are going to discuss in next. So we'll consider few example. Examples of UR to discuss, to show how looking at the behavior of effective potential, we can predict the trajectory of the particle. So maybe we will stop here for this lecture. In next lecture we will consider various examples of U effective and how we can predict the possible trajectory from the behavior of the effective potential. Okay, bye for now, and then in next class we will start with this discussion.